So you probably thought by now that we had done everything we needed to ever do about solving the maze and working out an appropriate path and stuff like that. And earlier this year, I was messing around with some code and scribbled down some notes and suddenly realized that actually, no, there is yet still a better way. So that's really what today is about. It's about improving the way that you store and use the maze information to drive your mouse. And I thought I'd look for a nice quote, and unbelievably, G.K. Chesterton had something to say about it. Now, I have not seen him at contests, but we live in hope. So let's just review the problem. I understand that you should all know about the problem, but for the sake of anybody coming later and watching a recording, let's just cover some details. So we won't look at the maze itself, but consider that every maze must have a start and a goal. The goal may be an individual cell, or it may be a block of cells, but for the sake of this work today, we'll consider the goal to be a single cell. And you need a path from a given location to a target. And I distinguish between them because, of course, the current mouse location might be the start of the path that you need, and the target may be the start cell, or it may be a goal cell, or it may be some other arbitrary cell in the maze that you want to visit. And what you want your code to do is to find an optimum path to go from start to goal eventually, or from location to target on a kind of minute-to-minute basis. Second to second, of course, if your performance is up. And the most important thing about this path is that it must be safe to run at speed. We've talked quite a lot about how to find a path and how to get to the goal and all that kind of thing, but we haven't really given much thought, I think, to how to guarantee that that path that you want to run is safe and doesn't go through unvisited cells or unseen walls or anything like that. And that's actually slightly more tricky than it may at first appear. And of course, time is limited. You really want all this done quite quickly. Ideally, you would like to be able to solve the maze, generate a path in the time it takes for the mouse to get from, well, certainly from one cell to the next, but maybe in the time it takes for the mouse to move 10 or 20 millimeters. I spoke once to a contestant in Japan about how he generated his final path, and he used a variant of Dijkstra's algorithm on a half-size maze, 32 by 32, and I asked him how long it took for his algorithm to run, and he said 17 seconds, which was a little upsetting. His rationale was that by the time it was running, by the time the mouse found its way back, it had worked out how to get to the goal again. And he acknowledged that it could be improved. So when we store details about the maze, and I understand that there are other ways to do this, but the most common way is to use a little bitmap. And although we duplicate walls doing it this way, it makes the code an awful lot simpler, right? You can pack it down to 1 bit per wall and no duplications, and that's all very clever. But even the Arduino has enough resources not to need to do that, and your code is faster and simpler to understand if you don't. So we would typically have 1 byte per cell, and we'd mark out 1 bit per wall direction. My convention is to number them like this, so that the north wall is bit 0 and so forth. And then we can, in any given cell, we can describe the walls as a simple single byte value. Binary 1110, or E is what you'd see in the start cell, right? So you've got a west, a south, and an east wall, and nothing to the north. And the corresponding cell above, which in my method is cell 1, would have a wall to the west only, so it would have a value of 1000 or 8 in hex. But my aim really is to keep this as simple as possible. There's just no point in making life more complicated than you need to, usually. So when you start off, you need to set all of the walls as being absent, add known walls for the perimeter, and known walls for the start cell. Because not everybody does that. They just zap all the walls in some cases. But since you know there should be walls around the perimeter, it seems sensible to me to mark them in to save you running off the edge of the world in your software. So I always mark them in. For me, the start cell is 0, and I use a single goal cell for the algorithm, which for a classic maze would be 7-7 or 8-8. And by 7-7, I mean 7 cells across and 8 cells up. So it's an XY coordinate. And we set the robot target to the goal. So far, so good. How does the mouse explore? Well, it has to move from cell to cell. Every time it encounters a new cell, the walls must be added to the map. And something which is often overlooked, for me at least, walls never get removed. They're only added. If you see a gap, you don't say, oh, there used to be a wall, but now there isn't. Right? It's simpler to just always add them in. And then that obviously leads to the frequent claim that you hear at contests of, oh no, it's put in a wall that shouldn't be there, and then bangs into it, and that's that. Nonetheless, that's the rule. At every step of the explore, planning is optimistic. That is to say, any decision you make about getting to the goal and passing through cells that you don't know anything about, your assumption is always that you can do that. And then as you get into those unknown cells, you discover that's not right, and so off you trot in some other direction. But optimistic path planning is how you do the exploration. There really isn't anything else you can do. Now, the problem is that when you get to the goal, you've gone by some roundabout route, which depends on what you discovered as you were doing it, and your route that you have taken is very unlikely to be optimal. It may not even be very good. And more importantly, it's unsafe. Right? So if you just drive to the goal, have a look at what you know about the maze, and then make a map and make a route, that route almost certainly goes through cells which are dangerous. That is to say, you don't know what's going on in them. So this is where it gets slightly harder to see, and my apologies if you're sat out in sunshine with a tiny laptop, but you know, what can I do? This maze is how we start, and if you can see the characters on there, if there's a problem, tell me and I'll wiggle the mouse around and try and point stuff out. But the M is the mouse position, bottom left. Poor old David squinting in the sunlight now. The X's represent the path going through unexplored cells, and the G is the goal. All right? So off we set. And after making a few moves, the mouse has discovered some walls. It's recalculated a new path to the goal. And this path is still optimistic. You can see that from the start to the current mouse position, there's some little kind of arrows which indicate the direction that you would take in each cell. But still, the X's say, this is my best guess of how to get to the goal, but I know that those cells are not safe. So one single step of exploration onwards, which will move the mouse north into the cell just above, and you discover two walls, and all of a sudden, everything's gone crazy. The optimal route, or rather the route that you think should exist between start and goal, still goes through a whole pile of unexplored cells, but now your mouse is in some kind of hinterland where it doesn't really know what's around it except for the cells that it's seen. So what move is it likely to make next? Well, if you wish at this point, you could go back and find the first of those unexplored cells and set out again, but that's a waste of time. So what people do as a rule is they just carry on, right? They plot a path from where they are, and the mouse will move to the west and then carry on. And what I've arranged for in this simulation is to always show the current best route from start to goal. Not the route that the mouse is going to take now, but the best route from start to goal. So after an awful lot of messing about and discovering walls and turning back and all of the other stuff that they do, finally, after 127 steps in this particular maze, the mouse has found the goal. This maze, by the way, if you care, is the Japan 2007 Expert Finals maze. It's just my standard practicing with algorithms maze. Now, clearly, at this point, the mouse is able to find a way to the goal, right? It's there, so there must be a path, right? But if you just take your standard algorithm, it's a simple one in this case. It's just a kind of stepwise one cost increases 1 per cell. If you take your standard algorithm and try and work out what should be the best route, you can see that even now that path goes through an awful lot of unexplored cells. So let's say that you crashed at this point and you had to pick the mouse up, put it back at the beginning and set it off again. You couldn't do a speed run because your best guess at the path, the correct path, goes through a whole pile of unexplored cells. You've got no idea what's there. The only thing you can do at this point is to explore some more. And then the question is, how do you know when you've actually got an optimal route, one which you can safely run at speed without having to check the walls every single time? If you don't crash, what you will do is you will, generally speaking, simply change the mouse's target to the start cell and explore some more. And in this particular maze, with this particular algorithm, it takes us a total of 207 steps to get back to the start. Right, so we've explored out, we've explored back, we've discovered different cells on the way back, and you can see that the mouse has wandered around at the top of the screen there, found a whole pile of walls, but still it does not have a path which is safe to run at speed. Now, there are other strategies you can use at this point. Some people choose to do a run now with an algorithm that only uses explored cells. After all, there must be a route, and it probably is better than the one you first used. So you could choose to get a speed run in now so that you can get some points before you eventually crash or whatever your problem might be. Alternatively, you can carry on exploring back and forth from start to goal until you think you actually do have an optimal route. It takes, in this maze, for this algorithm, a further 160 steps to go out and back, and you still have a non-optimal route. To keep going back and forth until you get an optimal route takes 317 steps in total, which is an awful lot of wandering about, right? And this is where, in the days where you got penalized for your searching method, there's no point in doing a speed run now. You might just as well pack up and go home. It's taking you so long to find an ideal route that you can't possibly, you could teleport yourself and still not get a decent score. But there is now finally a route. The mouse in this demonstration, the mouse has stopped at the cell in which it finally worked out that it had an optimal route. So how does it know? How can you tell that this is an optimal route? I haven't marked on any of those cells which are not explored, but if you have a look in the kind of lower leftish area, you can see there's a whole bunch of places where the mouse clearly hasn't been because it hasn't put in any walls, right? So how does it know that there's not some faster way through there? How can you tell that you have finished and got an optimal route? Well, there are several techniques. One is to have an extra bit in your bitmap. And just every time you mark a cell, every time you visit a cell, you set that bit. Then you can tell your path generation algorithm only go to cells where that bit is set. And this will make you a safe path. So you can choose to either flood all of the cells and then make the path generator only use visited cells, or you may choose to use a variation on the flood where the flood only allows you to actually mark visited cells. Either way, these are special cases, right? You've already got an algorithm that does this, and now you have to do something different. You have to add an extra rule that says only go in visited cells, either for the path or for the flood. It's simple, it's reasonably straightforward, but it complicates the algorithm slightly, and you have to be a little bit careful about what's going on. An alternative is to add an extra flag for each wall. So we've still got the 4 bits for the walls, and then we have another 4 bits which say, I have definitely seen that wall, or space, as the case may be, right? So you've not taken up any more storage. You have made life more complicated in terms of software, but now, better than individually visited cells, you can now say, I want to know if my path goes through this particular wall and whether or not it's really there or whether it's really a gap. This is the method that Decimus has been using for a while. It works very well, but it is a bit of a pain. The code looks unpleasant. It's all full of, tests for how do you know if a wall is there or really not there or just not seen yet. And it works well, but the code's just kind of scruffy. So now, having reviewed all that, onto the easier way. Anybody, before I do that, has anybody got any questions or issues with stuff so far? No? Okay. So a different way of looking at it is to consider that you record 2 mazes, an open maze and a closed maze. The open maze begins with no walls in it at all, except of course for the boundary. Whenever you find a wall, you add it to the open maze. So the open maze gradually gets more and more walls as the explore goes on. Note that the open maze always has a path to the goal if there is one. It's optimistic. The closed maze starts off with all of the walls filled in, except the one just to the north of the start cell. Every single wall is present. And as you discover gaps, you add the gaps to the closed maze. Now, at the start, obviously, there is no way to get from start to goal through the closed maze. Everything's got walls in the way. When you finally get to the goal, you can use the closed maze to plot your path, because once the goal's been found, that closed maze is always safe to run. And this is a really, really important point, right? The open maze is optimistic and always unsafe until you've found an optimal route. But the closed maze is always safe to run through. So let's have a look at how that works. We've got our open maze on the left and our closed maze on the right. And this is the initialization. This is the same maze as before. It's the Japan maze. And you can see the open maze has no walls, the closed maze has all walls except for the start cell. So we'll go and explore to that first place that I stopped before. And now you can see that the open maze has got some extra walls added, and the closed maze has got some extra gaps added. Carry on until we find the goal, and now you can see the use of the closed maze. Whilst the open maze has this optimistic path that goes through unexplored cells, the closed maze, you could, if you picked your mouse up and brought it back to the beginning, you could do a speed run now. It may not be a terribly fast speed run, but you could do one, as long as you use the closed maze. And at any time, you can run through the closed maze. There are plenty of practical contest mazes where by the time you've got to the goal, you may very well have found a nearly optimal route anyway, and you might just as well try and run it. And under the old rules with the search time penalty, sometimes that was a good strategy. It was a good strategy for a lot of APEC mazes. Go to the goal, come back, and immediately run with what you've got. But you do need to have a safe path. So we do a bit more exploring. I should say at the bottom left there, you can see the open cost, if you can read that, of 54. That's the number of cells taken to traverse the maze with an optimistic, unsafe path. When we finally got our optimal path again, you can see that the open cost has gone up, and that the path in the open maze and the path in the closed maze should be the same. And although I haven't put it in this demonstration, the cost in the open maze and the cost in the closed maze, that is the number of cells, is the same in both cases. That is how you know you've finished. When the cost in the open maze is the same as the cost in the closed maze, you have an optimal path. So you have to flood it twice, right? But because the flooding is simpler and was never hard in the first place, that's not a terribly big deal. It's much easier than going through and checking all the walls and all the rest of it. You've got to flood it to do that anyway. So you might just as well do it twice for the simple case. When the cost is the same, the exploration's done. Right, so to recap, you explore using the open maze. That always gives you an optimistic path to the goal. But those paths are unsafe. At any point after you have found the goal, you can use the closed maze to do a speed run. They are always safe. Also, closed paths will improve over time as you do more exploration, and so at any given time during your searching of the maze, the path through the closed maze is optimal and optimal at up to that minute, and improves as you carry on. And when they're the same, the whole thing is done. Does anybody actually already do this? No.
No.
Okay. So how are we going to implement that? On the face of it, it's a problem now because you've got to store two mazes, right? An open maze and a closed maze. And that's what I did for ages, until my little epiphany. If you store two mazes, then you have to pass a pointer to the maze, right? You can have a single piece of code which will operate on any maze, but you have to tell the code which maze you're going to operate on, which is just a pointer, right? But it's still a pain, and you don't really want the extra messing around, the dereferencing of pointers and all that sort of stuff. You can do without. So what can we do instead? Well, we had these 4 spare bits, right? We only needed 4 bits to store the walls in a cell. We can use the other 4 bits to store the other maze. So the lower 4 bits are the open maze, and the upper 4 bits are the closed maze. So a completely unexplored cell will have the value, the starting value F0, 1111000. If I've not lost count. So it'll have all walls in the closed maze, nothing in the open maze, nice and straightforward. If at any point I want to have a look at the walls in a maze, I can choose the closed maze or the open maze by simply shifting the contents down 4 bits or not shifting them. And if that number is a constant, I always do the shift. Right, in the code, I always do the shift. And if that constant happens to have the current value of 4, I'm looking at the closed maze. If it happens to have the value of 0, I'm looking at the open maze. Right, so my code is always the same, and there's just some global constant somewhere which says whether I'm currently looking at the open maze or the closed maze. And this is now true for all of the maze flooding and all of the path generation. I select the maze simply by changing a constant value from 0 to 4, and nothing else changes in the code. And since a bit shift is usually a fairly efficient operation, it doesn't make much in the way of performance difference either. So if I had given my directions numbers, north is 0, east is 1, south is 2, and west is 3, and so forth, if I wish, I can have a look at an individual wall with a bit mask. I can say 1 shifted left south, right, is a 1 shifted left 2 bits. And if I just do that, I'm looking at the south wall of the open maze. If I shift it left south plus 4, then I'm looking at the closed maze. And again, if that 4 is a constant, so it's 1 shifted left south plus maze type, let's say, and maze type happens to have the value 0, then it's the open maze. If maze type happens to have the value 4, then it's the closed maze. So again, the code is the same, just this one number changes. In my code, if I want to test for an exit, I can write a function to do this. This is pseudocode. Don't copy this into anything, it won't work. So I can have a function called hasExit, and I give it the cell that I'm interested in, the direction I'm looking, and what maze type I'm using. And then away we go. Right? So I create my bit mask and it with the current contents of the map. And if that's a 0, I've got an exit. Honestly, it could not be simpler, I suspect. I hope. I think. Now, what are we going to do to flood the maze using this technique? Well, we'll start off with some kind of function called flood maze, because that sounds reasonable. We're going to give it a target cell and a maze type, which again will be 0 for the open maze, 4 for the closed maze. First thing to do is to initialize the whole of the costs array, that's just another 256 bytes for a classic maze, to some maximum value. 255 is convenient, or whatever the maximum integer, unsigned integer is that you can store in there. We set the cost at the target to be 0. And we add that target cell, not the value, but the actual, the address of the cell. We shove that in a queue. Then we process the queue, right? There's one cell in it, so we take this cell out from the queue, and that's where we're looking at now. We work out what the cost is for the neighboring cells, and if we're just using a simple Manhattan flood, the cost will be 1 more than whatever was in that cell. And then we just run around all 4 directions. And for each of those directions, we say, if there's an exit in that direction, and we've already seen this is a trivially simple function, if there's an exit in that direction, what are we going to do? We find out what it is. So there's just a neighbor calculation. So it could, the cell to the north or the east or the west, that function will be dependent on how you store the maze. Derek stores his in a different order to the way I store mine, for example. So you work out what the neighbor address is, and then we say, if the neighboring cell looks more expensive than our current next cost, we just replace it. And then we add that cell to the queue, and that's it, done. right? It'll loop back round. As long as there's any cells left, we haven't finished. And when we've taken all of the cells out of the queue, the job's done. And this code has just been anonymized from a C function, which is exactly the same. And it wouldn't be much harder in any other language, really, as long as you've got a queue available. And you can write the other functions. It's really quite straightforward, I think. So a couple of extra thoughts. It's very easy when dealing with the maze to think in terms of the walls, but actually the mouse isn't interested in the walls. Actually, it's interested in the exits. It actually wants to see the gaps, right? It can only drive through the gaps. There's no point in knowing about the walls. You have to know about the gaps, but you have to know that they're real. If you care about whether or not a cell has been visited, and this is your homework, right? This is left as an exercise to the reader. If the open cell data and the closed cell data is the same, you have seen that cell. And you need not actually have been in it. You could have circumnavigated it and discovered that information, and it will still work. And that means that there is a circumstance under which a safe path can still go through an unexplored maze. So this is the qualifier from Japan 2007, and after all of the exploring is done, you can see the little yellow splash there is where the safe path goes through a cell which has not actually been visited. But it will still be safe, because we have seen those two gaps. We don't care about the walls, we've seen the gaps. That's it.
Okay, thank you, Peter. Questions, I guess, first for Peter.
I've got one.
Yeah, Rob.
Have you considered heuristics? While you were talking, I wrote down 4 heuristics. Do you want to know what they are, or have you already thought about them?
Well, at the moment, explain what you mean by a heuristic for this.
Right. So, obviously, if you know you've explored enough cells to know you've definitely got the shortest path. So you were talking about you might decide to do a speed run, for instance, ahead of that. So, for instance, if your closed cost is approaching your open cost, maybe it's good enough to do a speed run.
Yes. That's sorry, just to stop you there, because rather than deal with them all at once. Yes, my current code does or has something very similar to that, and it says, bearing in mind that I use a different and more complicated flooding method, right? Because I want to take into account how long it takes to traverse straits and that kind of stuff. But bearing all that in mind, my current code says if the safe cost is close enough to the unsafe cost, there's no point in wasting time trying to improve it, right? I care less under Japanese rules, but under APEC and former UK rules, I certainly would say, if it looks like I'm only going to get, a 5% improvement in runtime, do I really want to be spending the next 5 days trying to find it?
But it's not just that. I mean, there's a risk. Every cell you visit, the risk of crashing, even at slow speeds.
How dare you?
I'm sorry, Peter. I know your voice are perfect.
Yeah, yes, you're right. The longer you carry on, the more your chance of something going horribly wrong. So yes.
So the other ones I've written down were, if you're taking too much time, I mean, if you've got a 5-minute window or then after 3 minutes, you might go, right, okay, I'm getting close, let's do a speed run anyway. So have some sort of heuristic there, which I think you mentioned anyway while you're talking. The other one is, which is interesting to do with a closed path, right? If it's got high cost segments, and this is why we use the word cost rather than cell count. If it's got high cost segments, then you might want to do some more searching. A fuzzy logic type thinking. Whereas conversely, if there's no high cost segments, maybe you should just run it right away. Even if it's a long path, it might be that if your mice is really good at straights, if it's got a load of straights and no high cost segments, then now I don't know. Once you flood filled, you'd have to go through and somehow divide that up down into segments and figure out.
Hang on. Let me stop you then, because the cost that I talk about is cumulative. So in every cell, the recorded cost is the cost from that cell to the goal.
Agreed. But you might also be able to. You might also be able to plot.
That takes into account things like run length costs.
True, but if you've got, say, if your mice, it's poor at sort of comb sections, right? And even though you've got your costies, you might, as well as doing an entire end-to-end cost, you might say, well, there's a risk of these particular types of features, and if you plot it and get the mouse to analyze, there might be a water level on particular features that you say, right, I'll run them if I have to run them. So you're doing a risk analysis on each segment as opposed to just looking at a cost level.
You can certainly do that, and I do that by weighting the individual maneuvers. I don't weight a cell depending on whether it's dangerous to run, so the combs are dangerous, but you could, right? You could say, this cell has no walls, and so I don't have any steering guidance, and so I'll give it an extra weight. That still ends up in the accumulated cost, and it would, given a choice between turning left into a cell that's got a dangerous feature like a particular kind of turn that you don't like, or no walls or something like that, as against another one, if you have weighted this cell a little bit more, then the accumulated cost builds faster, and you wouldn't do that. So yes, all this can be done, but it's a layer on top of the basic idea that I'm kind of
yeah. No, I thought just having closed paths as well as open paths, it struck me that suddenly you've got a set of data you can mine beyond a simple end to start to target cost. Sure. You could do it on a you could analyze the path to see how risky it is versus search it, which has got risk. I mean, I'm not sure we could quantify the risk of particular features for a particular mouse, but still, it sort of gives you stuff that you can't even guess at with just an open mouse. I'll stop talking now for the first time ever.
Any more?
Any more, Peter?
Yeah. Could you? Obviously, you're always going to end up with the 4 bits of the closed maze are going to be the same as basically the inverted normal maze.
No, not inverted. They'll be the same.
Why would they be the same? If you've got of course. If you've got a gap, so they'll be the same. So if they're going to be the same, why can't you do the same calculations without recording them?
Oh, because they only end up the same.
Yeah.
They only end up the same because of the way you have recorded the maze. And I didn't put in the recording business, but when you get to your sensing point and you have a look and say, oh, there are these walls here, then when you add the wall information to the maze, you set a bit in the open maze for a wall present, and you clear a bit in the closed maze for a wall absent, right? Which goes against what I said before, but that's before we're talking about the
right. And but when it was cleared in the first place,
right,
there's a bit there already.
Yes,
so
you initialize it to F0, and when you see a space, you clear the closed maze bit, and when you see a wall, you set the open maze bit. You can do it quite efficiently. But that means that they will eventually converge, and you're really only storing data on a wall-by-wall basis rather than a cell-by-cell basis.
Yeah. Okay, that's interesting, because the algorithm we've got in Pick 1 Turbo does a lot of that stuff, but it doesn't do it in that way. And as you say, you need to sort of work out your route and then put another algorithm on top of that, and then another algorithm on top of that, and you sort of build up, and you end up with the same thing. So it can create routes that go through dead cells that that it's never been to, and know that they're safe. But yeah, that's an interesting way of doing it.
Okay, Peter, thank you. Brilliant. I have to say the only one I've written is for the Pick One, the software that I put in the Pick One, and that was a bit more simplistic. But I did look at walls, so keep the individual track of each wall. So you may not visit a cell, but you'd still know the state of all the walls, all the gaps in that cell. But usually, I was so happy to get to the middle that all I wanted to do is get back and do it again before I ran into a wall.
Well, it turns out if you compare whatever code you've got now with doing it this way, this turns out not really to be significantly more.
No, I think it's simpler.
The only because you've got that, always got that exact same calculation, right? And you just pass in a number, 0 or 4, and the calculation is always the same. There's never any decisions to make. I once read a nice thing on programming which says that you should always try and get rid of all of the if statements if you possibly can, and this does that, right? There's no decision to make. You just set a number and the job's done. And so because all that makes things much simpler, the only significant change that you need to make after that is when you do the initial mapping, and that's the setting and clearing of bits and sensors, and that's a relatively trivial thing to do.
No, it's very tidy. It would reduce quite a lot of the conditional statements that you see kicking around in a lot of these searches. And the fact that you could measure how close you are getting to the optimum by looking at the difference between the two costs, I think is... so if you're running out of time, entry time, you can just say, okay, cut and run, do a run now. Lovely. Okay.
Peter, have you actually coded this and tried it, or is this still theory?
I haven't put it into the mouse because I still haven't bothered to put my maze back together, but the code that the diagrams, they're all running in a mouse emulator, and I've tested it against loads of mazes, and really it's actually just a refactoring of existing code, so I have no problems with it working.
Cool. Any more? Last one for Peter, or are we done? Okay, Peter, thanks very much. Excellent again. Next up, we've got...